Welcome back. In example 2, we have the integral of 1 minus e to the x all over 1 plus e to the x dx. So in this case, we can try thinking about substitutions. If we let u equal 1 plus e to the x, for example, well, the derivative of that is e to the x, which we don't quite see on the top, unfortunately. There's not like an e to the x dx. Now, there are a bunch of options that we have here. We could break this up into two integrals, one over 1 plus e to the x, and then minus e to the x over 1 plus e to the x. And that would help with the second integral if we did a substitution of 1 plus e to the x. But then we kind of get stuck. We don't really see the derivative right there appearing with the dx. Now, there is something we can do. We'll talk about that in a little bit. But what I want to do here is try just letting u equal e to the x. The du doesn't appear with the dx again, but let's see if we can handle that. Let's just try to follow through with the substitution. After I scratch my nose. So if we let u equal e to the x, the du would be e to the x dx. Now, the interesting thing about e to the x is when you take the derivative, you just get e to the x still, which was the original u that we substituted. So we were going to replace the e to the x with u. But here is e to the x again, so we could replace it with a u if we wanted to. In fact, we could take this e to the x, divide it over to the left side to be with a du, and then replace the e to the x with a u. So we end up with 1 over u du equals dx. Now these variables are separated. We've got the u's on the left, we've got the x's on the right, and if we replace then the dx with 1 over u times du, that does the complete replacement of the x's, at least that part of the x's, into u's. So, and that's great because, you know, the whole thing about substitution is we want to be able to substitute all of the x's out into u's in order for the substitution to work. So let's see what we have so far. We have 1 minus u over 1 plus u times 1 over u du. So the e to the x's got replaced with u's, the dx got replaced with 1 over u du. Now we have an integral that's all in terms of u. It's all about u. All right, so let's take a quick step to simplify this. We have 1 minus u all over, and then I'm going to write u times u plus 1 du. Now off to the side, so when we look at this, we see this fraction. We see a polynomial on top, we see a polynomial on the bottom, and immediately you should start thinking about 7.4. So the partial fraction method. In fact, the bottom is nicely factored for us already. That's why I didn't distribute the u in. We like to have the bottom factored. So what we're going to do then is break that fraction apart into some smaller pieces using the partial fraction decomposition method. So we're going to have this break down into two fractions, one with a u on the bottom and another with a u plus 1 on the bottom. We'll multiply through by the LCD. We'll get 1 minus u equals a times u plus 1 plus b times u. So here we multiply both sides by u times u plus 1. And now we can plug in a couple of values of u to get rid of these undetermined coefficients a and b. So if we want to get rid of, if we want just a, we want to solve for a, we have to get rid of b, so let u equal 0. If u equals 0 on the left, we get 1. On the right, we just get a, so a is equal to 1. And then to get rid of a, we let u equal negative 1. So on the left, we have 1 minus negative 1, which is 2. And on the right, the a term is gone because you have negative 1 plus 1, which is 0, and that goes away. And then you have b times negative 1, which is negative b. So b is negative 2. Okay, so now we know exactly how this fraction will break down. It'll be 1 over u minus 2 over u plus 1. Remember, you can always double check to see if the partial fraction decomposition worked correctly by turning back around and bringing these two fractions together. You want to get an LCD, so you multiply top and bottom of the first fraction by u plus 1, second fraction by u, and then you can see if on the top you simplify to 1 minus u. We're not going to do that here, I just want to point that out. You can always double check. All right, so now we can integrate term by term. We've got ln absolute u minus 2 times ln absolute u plus 1. There's a little implicit or a mental u substitution. Now we already have the variable u, so when we say u substitution, it's kind of a little confusing, but we could use a different variable like t or whatever we want. But it's a substitution technically, let t equal u plus 1, for example. But here we can do it mentally because there's not really anything, there's no side effect of the chain rule if we turn back around and take the derivative of our antiderivative. And so this is going to be okay. Okay, but now we have to go all the way back to x. So replace the u's with e to the x, and we'll have ln absolute value of e to the x minus 2 ln absolute value of e to the x plus 1 plus c. And we could box our answer right here, but we can take it one step farther, and it's probably a good step to take because it simplifies. The absolute values in front of the e to the x can be dropped. Same thing for the e to the x plus 1. Those can turn into parentheses. But here you would get ln of e to the x, and that's just x. Ln and the exponential base e are inverse functions. They undo each other, and so you just get x here. They sort of cancel each other out. So then you can drop these absolute value bars around the e to the x plus 1, because that's always positive. And at this point, we can box our answer. One more thing I wanted to say about example 2 is that you can also try letting u equal e to the x, or I'll write 1 plus e to the x. And you can try this as an exercise to see how you like this one. Try letting u equal 1 plus e to the x, and then for the top part, try solving this for e to the x. So you would get e to the x equals u minus 1. So when you're doing your substitution, you would get 1 minus, and then in parentheses, u minus 1, and then over u, because the whole bottom would turn into u, and then the dx, you would just have to figure that out. It would be like e to the x dx. So you can check to see how that would work out. One thing is you'd have to then convert the e to the x into a u minus 1 and see how that all plays out. You're still going to have to do some kind of partial fraction decomposition, but it'll look a little bit different, and maybe you like it that way instead. So this is another possibility. A lot of these integrals, as I mentioned, you can do multiple ways. Now there will be easier ways and there will be harder ways, but whichever way ends up getting you the answer is going to be a great way to do it. So eventually all roads should lead to the same result, same antiderivative. Sometimes the form might look a little bit different, but you should be able to get from one form to the other through algebra. But all roads should definitely lead to some kind of correct result. Okay, so I'll end this part here, and the next part we're going to take a look at examples 3 and 4. See you there.